Hello everyone, my name is Yiran. This is the last presentation of CS 520. I'm on topic 3, which is find prime factors of a number. So first, let's do a quick overview. If we are given a number n, we have to write an efficient function to print all prime factors of n. I'll go over the three sections in my speech, and I will take n equals 658 as my example. Let's start with the algorithm's execution. I have my example here just for my reference when I go through the steps. So the first step is while n is divisible by 2, we print 2 and divide n by 2. And then we repeat until n is not even. So here I have my example divide by 2, which is 329. And from step 1, we know that we have to print 2. And then as we know that 329 is odd, we stop for the first step. So after step 1, n must be odd, and let's call it n sub 1. In this case, n sub 1 is 329. And then let's compute the square root of n sub 1, and we'll get a number around 18 here. So let's start a loop for I equal 3 to square root of n sub 1, and then we compute the n sub 1 over I. If the number is divisible, we'll print I and divide n sub 1 by I. But if not divisible, we'll increase I by 2 and repeat the above sub-steps. So from here, we'll stop when I is greater than square root of n sub 1. I'll explain in detail with my example here. Since we have a loop start from 3, we put 3 in our denominator. However, we have a decimal number as a result, and this is not the thing that we want. So we increase I by 2, and we have 5 as our denominator. However, we still get the decimal number. And we cross it again, and we increase I by 2. So we put 7 as our denominator, and this time we get an integer. Therefore, we'll print 7 here. And just trust me, for the 3 dots here, it's just I plus 2, I plus 2, and I plus 2. It is really redundant, so I won't show it step by step here. And in the end, we have our I to be 19. So from here, we can see that 19 is greater than 18, and we'll stop here for our second step. Please note that I will call this 47 over here as my n sub 2, just in case that we mess up with the n over here. So the step 3 states that if n sub 2 is a prime number, and if it's greater than 2, then we print n sub 2. And from the last slide, we know that n sub 2 is 47, which means that it is greater than 2, and we also know that 47 is a prime number. Therefore, we print the 47 over here. And this time, we need to check our calculations. So 2 times 7 times 47, it is the n over here. We get the same number. So let's look at the pseudocode. I put the code in Java, and this is the method that I have. It is called prime factors, and we have an integer as our input parameter. So step 1, we have to find the prime factor of 2, which is the while loop here. The while loop states that we divide n by 2, and if the remainder is 0, we print 2, and then we divide the number by 2. Before we go to the next step, we have to notice that n must be odd at this point, which means n can't be divided by 2 anymore. So this step is to find the additional prime factors by looping. So this for loop here states that we have I start from 3, and the upper bound for this for loop is the square root of n. And each time we loop through the loop, we add I by 2. Inside the for loop, we have another while loop here. The while loop states that if we get a remainder of 0 every time we divide n by I, then we'll print I and we'll divide n by I. So from the for loop here, if we have I plus 2 greater than square root of n, what we want to do is to exit the loop and check for the prime number. So if a number is prime and it is greater than 2, then we'll print out the number. And in our case, we have n equals 658, and I plug in the 658 here, and then this is what I get from my terminal window, which is actually the same as here. So now let's consider the big around time. Here I have two cases. The first case I pick is n equals 256. O 256 equals to square root of 256, which is 16. And the number 256 can be rewritten as 2 to the power of 8. And from the method that we had before, this means that there are 8 iterations. Therefore, we have the T256 equals 8. So from here, we have our big O to be 16, and our T to be 8, and O is greater than T, and therefore it is true. The second case I have is the large prime number, which I pick 257. From the calculation, we know that O 257 is around 16. So from the algorithm that we had before, we know that the T 257 iterates from 3 to around 16. And in this case, it iterates 7 times. So there are 3, 5, 7, 9, 11, 13, and 15. Therefore, the T257 equals 7. So the O257 equals 16, which is greater than the T57 equals 7. And in this case, it is true. Here's my reference page. Thank you for listening and have a nice day.